Uh, it's a pleasure to have Waseem Bakr. Did I pronounce your name correctly?
Yeah, that's right.
So Waseem was did a PG with Marcus Greiner in Harvard, postdoc at MIT, and now is an assistant professor at Princeton. And he's doing great stuff with cold atoms, which I guess we'll hear about right now. So Waseem, the floor is yours.
Yeah, it's been an associate actually for 1.5 years now.
Oh, okay.
Okay, so it's a pleasure to be speaking at the center. I saw a lot of the wonderful stuff on your website. I wish I could be there in person, but under given circumstances, I guess Zoom is the best we can do. Yeah, I'm going to tell you about the experiments we've been doing at Princeton with quantum simulation of Fermi Hubbard models using fermions and optical lattices. Okay, so the overall theme of these the experiments we do is trying to understand the behavior of strongly correlated materials. And there's a lot of examples, of course, in condensed matter, like these high temperature superconductors or fractional quantum Hall systems, where, let's say, the electrons or the spins are strongly interacting with each other. And it's very difficult to understand what's going on with classical computer simulations. So here's an example of a particular material, this high temperature superconductor. You can see there's under the hood a lot of complexity on the microscopic level. And it's almost impossible to capture everything that's going on in there. But typically what theorists do is try to capture sort of the essence of what's going on with a simplified model like this Hubbard model that I'm going to be discussing today. Now, of course, in this modeling step, a lot can go wrong. But let's say we got to this modeling step correctly, then there's still the problem of solving the model in the sense of, let's say, getting a phase diagram or extracting something about the dynamics of the system. So here we have to deal with the quantum many-body problem. The Hilbert spaces are enormous, and classical computer simulations are very difficult, as I was saying. So the solution was proposed a long time ago by Richard Feynman, which is this idea of using quantum simulators which are essentially systems that are very tunable and versatile. You can essentially use them to engineer the Hamiltonian of a quantum system from the bottom up, and then use them as a tool to simulate the physics of the system of interest. So there's a lot of different quantum simulation platforms, many of which are being studied in your center. Our favorite platform is this synthetic atom, these cold atoms and optical lattices. So what do I mean by cold? So here's the temperature of this room. So we're about 9 to 12 orders of magnitude lower in temperature. And the reason why we need to cool to these very low temperatures is that these gases that we're working with are very dilute. If we increase their density further than the values we're working with, they would typically undergo recombination processes. So we're restricted to spacings between the particles on the order of a micron or so. And that means that we need to cool down to temperatures below a microkelvin in order to observe quantum degeneracy effects for these wave functions of the atoms to start to overlap, and then we can start seeing these quantum effects. Okay, so how do we get there? Well, there's a long history in this field of cold atoms. There was a Nobel Prize for these gentlemen here for laser cooling and trapping. So here you can see a cell phone image of a cloud of trapped atoms in my lab. This is a cloud of lithium-6 atoms, which is levitated in a vacuum chamber using lasers and magnetic fields. And these atoms are cooled within a few milliseconds down to temperatures on the order of a millikelvin. And if we want to cool them, so at that point, so these billion atoms are scattering so much light that you can, like I said, you can just see them by eye. It's actually a beautiful red color for lithium. And if you want to cool them further, you really need to stop this light scattering. So you want to load them into a conservative trap, as these gentlemen taught us. And And so this is an example of a cloud that is trapped in what's known as an optical dipole trap. You can think of it very similar to the optical tweezers that people use in biology. So if you want to cool this cloud, then you just undergo evaporative, you can make it undergo evaporative cooling, and then at some point at a temperature scale on the order of a microkelvin, you achieve a degenerate Fermi gas for this isotope of lithium. Is the, let's see, do you see the pictures of yourselves when I do this?
Pictures of whom?
Okay, you're not seeing your own video feed. I just want to keep some video feed in case like I get disconnected because I'm getting zero feedback. So
okay, so there is no.
This is not overlaid on your slide. On the slides, good. Okay. Okay. So now we have this degenerate gas of fermions, and it's in 3 dimensions. They're in the continuum, and we would like to start to use them to model something like a solid in condensed matter. So the idea now is we want to create a band structure for these atoms, very much in analogy with the electrons in a crystal. So what we do is we use a tool called an optical lattice. So basically, you create standing waves of light with lasers. These can be created in arbitrary geometries in various dimensions. And the analogy here is between the atoms in this optical lattice. They play the role of the electrons in the solid, and then this optical lattice is playing the role of the ionic potential for a solid. The spacing, of course, is much larger in our systems between these lattice sites. It's typically on the order of a micron, the wavelength of light. So that's about 4 orders of magnitude larger than what you have in a solid. And also the atoms are, of course, a lot heavier than the electrons. And what this means is that the dynamics is much slower in our systems, typically on the order of milliseconds. So it's easy to observe. And at the same time, the temperature scales, like I said, are much lower. The energy scales we work at. Okay, so this. So why would you want to work with a system? Well, the first thing is, as I said, we can build up these Hamiltonians from scratch. So you can engineer lattices of arbitrary geometries. You can control the interactions in the system and the tunneling and other microscopic parameters, even in real time. So for example, if you just tune the intensity of the laser beams, you can tune the lattice depth and then control the tunneling in the system. These are very clean systems, these lattices. If you wanted to study this order.
I'm sorry, can I interrupt? Can I ask a question? What's the blue curve and what's the red curve?
This blue curve here?
Yeah, what's the blue and what's the red?
Oh, this is supposed to
And the black, I'm sorry.
The black is the lattice potential.
Which is what? The light. That's the...
Yeah, that's the standing wave of the light that we're creating. So it's basically you're just taking a laser beam, bouncing it off a mirror, and it creates an intensity pattern.
And it's a standing wave.
Yeah, and then the atoms experience the standing wave, this intensity, as a start shift. So they experience a modulated energy landscape, which is playing the role of the energy landscape that the electrons feel in a crystal. And then the blue is just supposed to denote the wave function of the electrons, so the sort of the Bloch waves.
And the atoms are attracted to the region where the field is large by the same effect as in tweezers.
Yeah, exactly.
Thank you.
Yeah, but please feel free to ask questions at any point. I'm not sure what the various backgrounds are. Okay, so yeah, so basically we have this model which is highly enlarged, and we can control everything in it. And this large spacing is advantageous in one particular way for the Stoke, in that we can actually probe the atoms in the system optically, right? Because we can, they're spaced by a distance on the order of microns. So if we have a diffraction limited microscope, you can actually go and image the individual lattice sites and look at the atoms. So if you have a strongly interacting system, living in this optical lattice, you can just take a snapshot of the wave function of the system, or let's say projection of the wave function on a particular realization of density and spin. You take a snapshot of it, and you can extract all sorts of correlations that are in the system in a way that you wouldn't be able to do in a solid state system. Okay, so it's very much like you would imagine like doing in a theoretical simulation. So here's an example of this. So these are these atoms living in this lattice. So before we took this, each one of these green dots is an atom. And before we took this picture, this was a quantum mechanical system containing roughly 1,000 atoms or so. Each of these atoms was delocalized over the lattice. There was tunneling happening. They're interacting strongly with each other. And then when we take the image, they get projected on a particular realization, and we take a measurement. Now, when we're taking this measurement, of course, we want to scatter a lot of photons so that we can resolve the atoms on the camera with good signal to noise. And we have to, we're starting from the lowest band of the lattice. So if you imagine an individual lattice site, we're sitting in the lowest energy level. Then when you start to scatter photons, the atoms heat up. And so in order to keep them frozen on the sites while we're imaging, we have to provide some laser cooling. And in this picture here, we deliberately sort of messed up the laser cooling so you can see some classical hopping while we're taking this video. But when we're actually trying to do physics, we have these systems really frozen while taking the image, and we collect about roughly 1,000 photons from each atom on the camera. And so we can reconstruct with high fidelity whether we have an atom on a site. And now with these more recent microscopes, you can even tell what the spin of the atom is. Okay.
How do you prevent the measurement from actually interfering with the state that you're trying to probe?
So if you're just trying to figure out the density on a particular site, like I said, you don't want the atom to move during the imaging. So here, I mean, it's already collapsed onto a classical like density distribution. If you're talking about the spin, well, that's more challenging. So if you're trying to, let's say, you're encoding a spin within a hyperfine state of the atom is what we do, then the photons, yes, they do optical pumping processes and they would jumble up the spin. So the standard microscopes, like the one I'm going to talk about today, they don't actually measure the projection of the projected spin. But newer microscopes can do tricks like a Stern-Gerlach, let's say, in the third dimension, and then you can extract the spin.
Mm-hmm.
I do not seem to see any lattice or any periodicity in the background. Is this?
The square lattice, if you Fourier transform it, you can see it's the diffraction pattern of the square lattice. This is maybe, it's a little hard to see here. I mean, it's not this picture.
And the lattice spacing is what? Is like 5 times the size of the dots?
No, it's on the order. So we're barely, basically the spacing of the lattice is in this experiment is about 750 nanometers. And our diffraction limit is just above that. So we're barely resolving the lattices, the atoms on the lattice sites. But since we know that there is an underlying square lattice and we can fit the phase of this lattice, say, with some stray atoms that are in a sparser part of the cloud, you can overlay the grid structure on this, and then you can decide whether, with an algorithm, whether you have an atom on a site or not with a fidelity of about 99%.
Thank you.
So that's the platform. And now we'd like to study some physics with it. And there's an enormous amount of physics you can study with these systems, depending on how much you want to engineer these systems. But the natural physics that comes out, if you don't want to add additional ingredients, is the physics of this model called the Fermi-Hubbard model. So this is a model where we're imagining 2 species of fermions living in this optical lattice. These are, in reality, 2 hyperfine states of the atom. Like in our case, they differ by their nuclear spin. And we call them spin up and spin down in analogy to the states of the electron in a solid. And then we have these fermions moving in this square lattice, and they can, to very good approximation, they obey this Hamiltonian, where they can do one of 2 processes. They can tunnel between neighboring sites with this tunneling matrix element T. We can't have two fermions of the same spin sit on the same site because of the Pauli blocking, because these fermions have been cooled down to the lowest band. But we can have two fermions of opposite spin land on the same site, and that's described by the second term in the Hamiltonian. And then they would interact by an on-site interaction. And this is a strong on-site interaction, U. And we can actually control both of these parameters in the experiment. So we can control T by varying the depth of the lattice. So you just change the laser intensity in the lab. And you can actually, we have techniques to change U, the interaction energy, by changing a magnetic field in the lab. It affects the scattering properties of the atoms. So we can actually tune this ratio of U to T over orders of magnitude in the experiment. We can tune other parameters of the system. So you can also tune the density of the atoms in the lattice. Sort of what sometimes people call the filling of the lattice. We can tune the temperature. If we can heat up the system, or just let it at whatever ultimate temperature we reached after the evaporation. So essentially, we can probe all the entire phase diagram of this model. Okay.
Waseem, what is the kind of energy scale of the second band in each well?
Yes.
In U?
So we measure in units of kilohertz. So just you would have to multiply by Planck's constant to get the energy scale. So the tunneling, for example, would be on the order of a kilohertz. The interaction is about 5 kilohertz. The spacing to the higher bands is about a few 10 kilohertz.
Okay.
Okay, so the question is, how much of the phenomenology of the Cuprates does this Hubbard model reproduce? This is, of course, a question that people have been studying for decades, ever since here at Princeton, Phil Anderson proposed that this model might describe what's going on in these high-temperature superconductors. So this is believed basically to be a minimal model for what might be happening in these Cuprates. Of course, the real Cuprates are much more complicated, but maybe we can try to capture their essential physics with this model. And it's been studied for decades now theoretically, but we still don't know, for example, what the ground state of this system, of this Hamiltonian is. And even sort of in the normal state where it's not superconducting, higher temperature, there's still a lot of mysteries going on. So that's what we would like to understand with our quantum simulators. Okay, so we don't have a phase diagram for the Hubbard model, as I was saying. So we can maybe, for inspiration for this discussion, we can look at the Cuprate phase diagram. So this is a schematic of an experimentally measured phase diagram of a high temperature superconductor in the axes of temperature and doping. Okay, so temperature is self-explanatory. Let me say what doping is. So doping means we call a system undoped, or it would be at half filling. So that's when you have, on average, an equal number of fermions and lattice sites. That doesn't mean every fermion has to have a lattice site, just on average, they're equal. Now, if you take away some electrons from the system, or in our case, atoms, you would whole dope, or you can add more, and then you would particle dope. Okay, so this point here where we don't have any doping, that's called half filling. And the Cuprates are in a strongly interacting regime. So this interaction U compared to T, the kinetic energy, is large. It's on the order of 8. And so what that does is it suppresses density fluctuations in the system. You don't want to put two fermions on the same site because they'll interact strongly. So you arrange the atoms so that they are mostly one atom per site. That parent compound is called a Mott insulator. And there's, of course, quantum fluctuations on top of that. Now, if you cool the system further, so that's at high temperatures in the undoped system. If you start to cool the system further, then spin ordering kicks in, and you get a Heisenberg antiferromagnet. Okay. So there, basically, the super exchange processes between the electrons will arrange the system into a Heisenberg antiferromagnet. And both of these, the Mott insulator and the Heisenberg antiferromagnet, are seen in classical quantum Monte Carlo simulations on classical computers. So we know they're there for the Hubbard model. So where things get complicated is once you start to dope the system. So there, this gold standard for the simulations, the quantum Monte Carlo, suffers from something called the Fermion Sine problem, which practically means that as you get to lower temperatures, the simulations become impossible. And that's really where the interesting physics happens in the cuprates. So at low temperatures, you get a superconducting phase, the famous high temperature superconductivity here, the D-wave superconductivity. In the normal state of the cuprates, you have a lot of interesting regimes which are not Fermi liquid behaviors. So they're like the strange metal has anomalous transport properties. The pseudogap has gaps opening up in the system even before it becomes superconducting. So these are all behaviors that are anomalous, and we would like to understand them because people believe that understanding them is important for understanding the D-wave superconductivity. Okay, so that's the background. Let me show you now what we can do with this quantum simulator in terms of starting to study this physics. So first, I'm going to show you some of the phases we see at half filling. So actually, in our systems, so this gas is sitting in a lattice, and this lattice is created by laser beams. So these laser beams have a Gaussian profile, so they're finite in extent. And so you have the atoms experiencing, in addition to the lattice potential, they experience this overall trapping potential due to the trap, due to the laser beam. So basically, the density in the system is spatially varying. It's not fixed. Whereas in solid, you have a fixed electron density. Here, our density is highest in the center of the trap, and then it drops to 0 near the edge. So we like to think of them in a local density picture where we have a varying chemical potential. So the chemical potential is highest in the center of the trap, and then towards the edge, it drops. So in the center of, so now we can tune this central chemical potential by loading different amounts of atoms into the trap. So here in this picture, we've loaded actually enough atoms to get the chemical potential within the Mott gap, so that we end up with a Mott insulator in the center here. So a Mott insulator would have 1 atom per site. It's again hard to see because the diffraction limit is on the order of lattice spacing. But whenever you have a missing atom like here or here or here, we can see it. Okay, so we have a Mott insulator here, and then as you go towards the edge of the trap, you get into a metallic phase. Okay, so now if you try to push the chemical potential in the center even higher by loading even more atoms, you get into a band insulator where now the chemical potential is sitting in the band gap. And there we see pictures like this. So basically we get a Mott insulating shell over here where there's 1 atom per site. And then in the center, we actually don't see any atoms. And the reason for that is that when we have 2 atoms on a site, a spin up and a spin down in the band insulator, there are actually light-assisted collisions that happen within the first few photons of the imaging. And these atoms get ejected from the lattice immediately. And so the rest of the remaining, where like an atom would scatter 1,000 photons, here we would just see 0 from over the remaining time of the exposure. Somebody had a question? Okay. Okay, so basically this is a picture of the band insulator, or what used to be a band insulator before the imaging, and then surrounded by a Mott insulator. Okay, yeah.
So the single points that we see in the central region, these are essentially places where you had a defect or excitation?
Yes, yeah. Or the fidelity of this process of the light-assisted collisions was not perfect.
So what do you think? Is it like a real observation of excitation, or it's the fidelity?
I think in this case, it's mostly fidelity, because if you look at the temperatures we get for subsequent measurements for things like the antiferromagnet, we would not expect to see excitations. So this would mostly be imaging defects. Okay. We do have some trouble with light-assisted collisions. In other experiments where the traps are tighter, the light-assisted collisions are more efficient, and they see much cleaner band insulators.
What is the width of the Mott insulator region? That's like this, you have a multi-insular ring, right?
Yeah, so this would be on the order of 10 sites. I mean, it's controllable depending on how many atoms we load into the system. Okay, so now the next interesting phase to look at is this antiferromagnet. And as we were discussing before, in order to measure the spin without jumbling it up with these optical pumping processes, it's pretty tricky, but now people have perfected that in other groups. This is kind of old data from the early days of this in 2016, 2017. And there, what we were doing in these days was, instead of measuring the spin, what we do is we shine a resonant pulse of light resonant with one of the spin states, and that eliminates that particular spin state from the lattice. So we're essentially looking at, let's say, only the spin ops in the system. Okay. And what we see in the pictures is these kind of checkerboard structures here, like this one here. Now, before we blow away, if we take a picture of the system before we blow away the spins, then we would see this Mott insulator within this sort of region. You guys see my mouse?
You see the Mott insulator in the inner region, not on the ring.
Inner region. So this would be a Mott insulator in the inner region, and then a metallic phase at the outside. Okay. So in the inner region here, you have a Mott insulator, and that's where at low temperatures you expect to see the antiferromagnet. If you remember from my phase diagram, once you dope the Mott insulator away from half filling significantly, you lose the antiferromagnet. Okay, so it's only in the central region where you expect to see the antiferromagnet. And you see, it's not perfect, right? Like you only see this checkerboard in this region, and then in other regions you don't see it. And actually, you don't expect to see it everywhere. So this is for two reasons. First, this is a quantum Heisenberg antiferromagnet. So it has this Néel order parameter which can point anywhere in the block sphere. So only when it aligns with your imaging axis, with your imaging basis, would you see this checkerboard order. But in other shots, it might be sort of aligned perpendicular, and then you wouldn't see any checkerboard order. Okay, so that's one reason, the quantum mechanical fluctuations of the order parameter. So actually, even in the ground state, for example, if you look at the nearest neighbor correlations, you don't expect them to be more than 30% antiferromagnetic. And then the other reason is that we're at finite temperature. So the range of these correlations is limited. We're pretty hot compared to condensed matter systems, and so we expect the range of the correlations to be on the order of a few sites. And so the way we kind of analyze this more quantitatively is we take a lot of these pictures, and then we can extract the spin-spin correlations in the system at various site separations, and that's the picture you see on the right. So you can see the checkerboard order, and this we can analyze quantitatively. For example, we can fit the correlation lengths, and we can extract temperatures for the system by comparing to state-of-the-art quantum Monte Carlo calculations, and thereby we can put down a temperature for these systems. And so the temperatures we reach typically are on the order of 0.3 times the tunneling energy scale. So in solid state, of course, in solid state, the tunneling energy scales are way higher. So if you convert this to solid state temperatures, this would be on the order of 1,000 Kelvin. So this is a pretty hot system in solid state temperatures. Okay. Any questions so far?
Again, so are you measuring spin-spin correlations, or just measuring local spin?
No, these are spin-spin these pictures that you're seeing here on the right, that's a spin-spin correlation. So you take the picture of this spin state of projections on a particular, like let's say we're just measuring the spin ups, and then we're assuming, let's say, well, actually, we can this particular picture here is a proper SZ spin correlation for sites separated between like at various distances. But let's say to first approximation, you can think of why we can measure the spin is if you have a Mott insulator and you blow away one of the spin states, then the holes are the other spin state, right? So the holes are essentially, let's say, your spin down and your particles are your spin up, and then you can extract the spin-spin correlator. Now, of course, the Mott insulator has some quantum defects. So it has quantum fluctuations. So it has like these double on hole excitations that appear as holes in our pictures. So there's a hole correlator you have to subtract out of these correlators to get a proper spin-spin correlation, and we do that to get these pictures. But that's sort of a subtlety that we have to worry about. But I mean, the first approximation is just looking at particles and holes and labeling them as spin up and spin down. Okay.
One more.
So I have one question, just the temperature comparison that you gave with hopping. But I mean, how about if you compare it with the Heisenberg exchange of your system?
It's about a half or so.
Okay.
And maybe one more question on the temperature. What in the end limits the lowest temperature you can achieve technically in your system? What is the bottleneck?
As far as we understand, so we know that it's not so first we're preparing these systems through an adiabatic scheme where we're starting from this very low entropy gas, the Fermi gas that we prepare by evaporating and then turning on the lattice. So one question you could worry about is the preparation actually adiabatic? And it seems it is. So we can like load into the system, load it back, and we see we're not causing any excitations. So there's no issue of adiabaticity. It seems it's in the earlier stage of actually preparing the three-dimensional degenerate Fermi gas, or the two-dimensional degenerate Fermi gas in our case. That seems to be limited by the evaporation. And so I'm sure you know that this evaporation, like it gets harder and harder to thermalize as you get towards the evaporation. So we believe that evaporation stage is what's limiting our temperatures. So if you accept that the entropy at the end of this evaporation is fixed per particle, then you can try to work with this entropy and distribute it in your cloud to reach lower entropies within some region of the cloud. So this is called entropy redistribution. And that's something, for example, my lab and other labs are working on to try to reach lower temperatures. We're optimistic we can reach temperatures on the order of 0.1, maybe even lower times T with these entropy redistribution tricks. But that's kind of the state of the art right now is 0.25 T, 0.3 T. Okay. Okay, good. So I've discussed now this antiferromagnet, the Mott insulator, and I was planning to cover a lot more, but it's good we have a lot of questions. So I'm going to focus on one particular part of this phase diagram that's doped, and that's the strange metal. And I want to explain how we can start to understand that in transport experiments we're doing here. And there's been actually a lot of recent beautiful work using the microscope as a microscope, not as a sort of tool, as a way to measure the transport, to look at the correlations within these strange metals, but I won't discuss that. Okay, so this is kind of a bit more conventional condensed matter probe, the transport. Yeah. Okay, so what we want to discuss is the strange metal, and that's basically a metal that people observe in the cuprates, which has anomalous behavior in the resistivity. So before I discuss this strange metal, let me discuss what a normal metal is. So this is basically the Fermi liquid picture of a metal. So in this Fermi liquid, we have these quasi-particles, which are carrying the various conserved quantities like the charge and the spin and the energy, and they're moving around in the system and colliding with each other every mean free path or so. That's this L. And we can relate this through the Fermi velocity to a scattering rate, gamma. So this would be the momentum relaxation rate. And we know from basic freshman physics that this is related to the resistivity of the system through a Drude model. Okay, so if you measure the mean free path, you can link it to the resistivity. And in this quasi-particle picture, there are various bounds one can put on these quantities. So if you imagine, let's say you heat up the system, so you're increasing the temperature, then the mean free path will shrink, but then eventually there's a minimal mean free path that one can sensibly talk about in this quasi-particle picture. So you can't talk about a mean free path that's shorter than the interparticle spacing. It just doesn't make sense in the quasi-particle picture. Or maybe in the lattice system, you can't talk about a mean free path shorter than the lattice spacing. So this minimal mean free path is what people call the Montefiore-Regel limit on the mean free path, and correspondingly on sort of a minimum mean free path or a maximum resistivity one can expect in this quasi-particle system as you heat up the system. There's another prediction that one can make for these quasi-particle systems. By combining Fermi liquid theory with Boltzmann theory, you can predict how the resistivity behaves at low temperatures. And in a solid state system, the resistivity can come due to various reasons. It can come due to disorder, or due to phonons, or interactions between the electrons. In our systems, it's kind of very clean, because the only way we have resistivity is the interactions between the atoms. We don't have any phonons in the system because our lattice is this rigid lattice that's created using the optical lattice. We don't have any disorder in the systems, as I explained. So it's really just the interactions that are causing the resistivity. So we expect this T-squared scaling in a Fermi liquid. Okay, so
Hey, I'm sorry, can I interrupt? Aren't these particles neutral? So what does one mean by conductivity or resistivity?
so this would be transport of density, which we sometimes loosely call charge, but it's really density in our systems. Okay.
Okay, except it's not clear to me why is it related to the charge E squared.
I mean, there wouldn't be an E squared in our system. It's really just it's a neutral density, and I mean, you can still talk about conductivity, like transport for this density, right?
Okay.
Okay. So now let's contrast this with what sometimes people call this would be a good metal. Let's contrast this with a bad metal. So in a bad metal, these quasi-particles are destroyed and due to the strong interactions. And what people observe empirically in a lot of materials is that as you increase the temperature of the system, you go through this Montefiore-Regel point, and the resistivity does not saturate like you would expect in a quasi-particle system. So the resistivity just keeps going up. Okay, so there's a lack of saturation of the resistivity. So we don't have quasi-particles essentially. And then empirically, what one observes in a lot of these systems is that the resistivity goes linearly in the temperature. Okay, so again, it's not the Fermi liquid prediction, and that's very poorly understood. This is in the context of the cuprates. This is what's called the strange metal, this linear interior resistivity. People believe understanding the strange metal is important for understanding what's going on in the lower temperature physics part of the phase diagram in the superconducting phase, and this linearity is not even understood. What's the source of it? So we don't know whether it's like phonons, which would Boltzmann transport theory would lead to a linear interior resistivity, or it could be interactions. But then why would those cause a linear interior resistivity? So that's something we were interested in seeing whether we can answer that sort of question in the context of the Fermi-Hubbard model. Surprisingly, people hadn't looked at that before too much, whether the Fermi-Hubbard model supports a strange metal. Okay. So measuring conductivity in our systems is hard. We can't just stick in leads and measure like a current in response to a voltage. People try to emulate this in these systems. So there are some beautiful experiments from ETH Zurich where they try to engineer reservoirs and connect them with channels, and then you can sort of apply chemical potential difference between the reservoirs and look at the flow of the current in response to that. So it's sort of like the traditional way you would measure resistivity. But because our systems are so small, usually these experiments you end up measuring properties of the channel rather than the bulk resistivity. So we have to kind of go to more roundabout ways of measuring the resistivity, and I want to tell you what the protocol we developed for measuring the resistivity is. So rather than trying to measure the resistivity directly in these systems, we're going to connect it to a more microscopic quantity, which is this diffusivity. Okay. So there's this famous Nernst-Einstein relationship in condensed matter, which connects the two quantities. So the conductivity, which is the inverse of the resistivity, is the product of two quantities. One is the diffusivity that I'm about to explain how to measure, and the other is this compressibility, okay, how the density changes with the chemical potential. So that's something that the cold atom people have known how to measure for a while, and I'll explain how we do that later. But the diffusivity is really the new interesting part here. So the idea now is that we can not only image these systems with a microscope, but we can actually also project patterns on the lattice length scale on them through the microscope. So we can use the microscope in reverse. So here we have this chip, which we call a spatial light modulator. It's sort of like a projector chip. And when you shine light at it, you can create arbitrary intensities of light at the output. And you can take these arbitrary patterns of light and project them on the atoms. And they exert these Stark shifts. So they experience an arbitrary potential landscape. You can put the atoms in whatever potential landscape you want. Okay? So in particular, so one thing we wanted to do in this experiment is do a very clean measurement where the density is fixed, just like you have in condensed matter. So we can flatten the harmonic potential due to the Gaussian laser beams over some region of the lattice. And so we get a uniform density in the system. Okay, that's one thing we did. And then the other thing we did is we put these stripes on the spatial light modulator. So that's these stripes that you're seeing on the cloud here. And so we loaded the atom, this cloud adiabatically into the stripes, okay? So we still have the underlying lattice, but then on top of the lattice, we have this long wavelength pattern that we create, okay? So we have essentially a long wavelength charge density wave that we create with this projected light. And now what we're gonna do is we're gonna suddenly switch off this projected light and then let the atoms diffuse in the lattice. And from the dynamics of that, we can extract the diffusivity.
What is the wavelength of this charge density wave?
We can control it, so it's anywhere from a few sites up to the full system size, which in our case is about 30 sites diameter. Okay.
And the system equilibrates while this is on, right? I mean,
yeah. So we load it adiabatically into this charge density wave pattern, and so it's close to the ground state. And then from there, we're gonna just let it do sort of quench dynamics after we switch off this modulation. Okay. So here's a movie of what's happening. So this is at time equals 0. You have these stripes along one direction, and then very quickly, within a few hundred microseconds, the pattern equilibrates. And this elliptical region here is the region where we flatten the density profile, so we get a uniform density. Okay. So this time scale here corresponds to a time scale on the order of a few tunneling times, basically. Okay. Okay, so this is all happening in a strongly interacting system. This U over T is very similar to what you have in the cuprates, about 8. And the average density in the system is about 82%. So this is corresponding to a whole doping of 18%. And the reason why we picked these numbers is, well, we just picked them blindly, but they're similar kind of to what you have in the cuprates, where I showed you the superconducting dome, and above that there is this strange metal. So the superconducting dome occurs roughly at these dopings. Okay, so that's where we're expecting to see, if there's any strange physics, we expected to see it there. Okay, okay. So now what we did is we look at the amplitude of this modulation versus time. So this is this density modulation that we imposed at t equals 0, and then it decays over time. And so if you just look at the amplitude of this modulation that's fitted here versus time, it does something funny. It undergoes some sort of underdamped oscillation. Okay, and that's already not what you might expect. You might be used to diffusion, where this amplitude would decay exponentially in time. Here we're seeing a little bit of a bounce. Okay. Now, if you go, this is done at you're asking about the wavelength. So this blue curve is done at a wavelength of 5 sites. Okay. So if you go to a longer wavelength, like 10 sites, then you get more damped behavior. If you go to 15 sites, it's even more damped. And then at 20 site wavelength, it's almost completely damped. So this is starting to look like an exponential decay almost. Okay. So we wanted to, so basically what we're studying here is the hydrodynamics of this doped Hubbard model. Okay. And the question, so we wanted to come up with a simple model to fit this data. And the simplest model, hydrodynamic model you can imagine is just these two equations here. Okay, so the first is just the charge conservation equation. Okay, so again here, charge is in quotation marks. What we really mean is the density, as Yossi was asking. Okay, so you can talk about a current of the density and the density itself. So we have this conservation equation, and then the second equation we're adding here is a modification of Fick's law. So Fick's law is what you would use to describe diffusion, right? So diffusion would be that the current density is proportional to gradients of the density, and the proportionality constant is this diffusivity. So you would write J equals minus D times gradient of N, right? So that's Fick's law. And then if you, okay, so we clearly don't obey Fick's law because Fick's law would predict diffusion, which would be an exponential decay. So we need to modify it. And what we're saying here is that when we start with this charge density wave, the currents don't build up instantaneously as predicted by Fick's law, but they need some time to build up into their steady state value. So there needs to be some umklapp processes that lead to this steady state current. And that happens over some time scale or some rate. And this rate we call gamma. So this we would call the current relaxation rate. So if you look at this equation, when you set the left-hand side to 0, you recover Fick's law. Okay, so in the steady state, you recover Fick's law, but you reach the current that's predicted by Fick's law over some time scale. And so the rate with which you approach the Fick's law current is this gamma. Okay, and so if you combine these two equations, you get the equation for a harmonic oscillator, just the usual harmonic oscillator we teach in freshman physics. And so the damping is this gamma, and the frequency of the oscillator is k, the wave vector of the charge density wave, multiplied by square root of gamma d, which you would think of as the speed of sound in the system. Okay, so you see by varying this wave vector of the oscillation, the k, you can go between an underdamped case where omega is large compared to gamma, the frequency of the oscillator is large compared to gamma, to an overdamped regime. So you're essentially crossing from a sound mode to a diffusive mode. Okay, any questions about this? Okay. So now the next interesting thing. Okay, so basically we actually verified that this model works by fitting it, like I showed you, to the curves we have, and we can extract this gamma and d with just these two fit parameters. We can extract. We can fit all the curves at different k's, and we can extract the gamma and the d. So the interesting thing to do here is to look at the dependencies of these quantities on temperature. And
I do have a question. I'm sorry I bother you. So I understand the first equation was the equation of continuity. Yeah. So why instead of the second equation, don't I get something like Euler equation, something Newton's law?
So we're not writing. So you want to write an equation for the momentum here?
That's right. Yes. What happens to? There is no Newton's law. What
not is conserved because it's we have the lattice and there's exchange of the momentum with the lattice through umklapp processes.
I see. Okay.
Okay. So okay. So now we want to study the dependence of these quantities on temperature, and that's what we see in these graphs. So the diffusivity as you lower the temperature goes up, and the current relaxation rate goes down. And that's what you would expect at low temperatures, because at low temperatures, the Pauli blocking starts to close the scattering channels, and so the diffusivity has to go up. Okay. Let me, since I'm starting to run out of time, let me not comment too much on these behaviors, except that this diffusivity is behaving in a non-trivial way with temperature. And the other thing I want to say about it is also look at the temperature scale we're measuring over. So this is, for the condensed matter systems, it's sort of a ridiculous temperature scale. The lowest temperatures we can reach is 0.3 T, which I said corresponds to about 1,000 Kelvin. So this is kind of near the upper end of where people explore strange metallicity in the cuprates. Okay, the higher end, about 8 T, this would be thousands of Kelvin. So this is a regime where you wouldn't even, basically your cuprates would melt, right? But we don't suffer from that problem in experiments because we have this rigid lattice, so our lattice can't melt. So we can really explore regimes beyond what one would explore in a conventional solid state system. Okay, it's a regime which is purely theoretical in these Hubbard models. Okay, so we have a non-trivial temperature dependence for the diffusivity, and now the other part of the story is the compressibility, right? So you need these two ingredients to measure conductivity. And the compressibility we can measure the way I was describing earlier. So if you just put the gas in this harmonic trap, so this is a separate experiment now from the transport measurement. If you just put the gas back in the harmonic trap, the density profile is varying in response to the variation of the local chemical potential. So you can just take the derivative of the density profile and you can get, with respect to space, and you get the compressibility of the system, okay? That's these red points here. And unlike the diffusivity, which is related to unequal time current correlations, this compressibility is an equal time density correlator. It's related through the Kuba formula. So it's something which one can actually calculate reasonably easily with quantum Monte Carlo, and that's these green points, and we find very good agreement with the theory, okay? Again, the compressibility is behaving in a non-trivial way with temperature in these experiments. And usually in condensed matter, the compressibility actually is you're working at such a low temperature that the compressibility has saturated in condensed matter experiments. It doesn't exhibit any temperature dependence, while we're working in a regime where it does. So let me distinguish between different regimes. So let's say in the solid state, you work in the low temperature regime where the compressibility has saturated and any dependence of the conductivity has to purely come from the diffusivity, temperature dependence. We're working in what I call the intermediate temperature regime, where both the compressibility and the diffusivity are temperature dependent. And then one can also discuss a high temperature regime. There, the theory is a bit easier. And what one observes is that the diffusivity saturates, while the compressibility, you can do a high temperature expansion, and the dependence of the compressibility is like this, like 1/T. So if you go back to the resistivity formula I gave earlier, then the resistivity would be linear in T in the high temperature limit due to just the behavior of the compressibility, okay? So we're kind of exploring a regime between that of the solid state and the more trivial regime which people understand theoretically at high temperatures, okay? And so what we find is when we compute the resistivity, we find a straight line, okay? So this is the new discovery in this talk, is that we see a linear T resistivity within this intermediate temperature regime. So a strange metal in this intermediate temperature regime of the Hubbard model. And as I explained, this is something which we don't know how to explain theoretically, because this is in a regime where we don't have quasi-particles, so all of our favorite theories are out of the window. So all we can do really to explore this is just numerics. And surprisingly, numerics, because it's so computationally hard, it wasn't done before the experiment. It's only once we did the experiment that motivated us to collaborate with some theorists to do the numerics, and also later on there was other people that did various theories. So let me show you a few of the theories we explored. So this is called the finite temperature Landschaft. So this is on a 4x4 sites. We did an exact diagonalization. 4x4 sites is a very small system, obviously, but that's all one can do, simulate with these Hubbard models exactly. And there's a lot of finite size effects. So if you go to low temperatures, the finite size effects are severe, so you can only explore temperatures which are about 3 times the experimental temperature. So without any fit parameters, it lies pretty well on the data. So that's the exact diagonalization. This is what's called dynamical mean field theory. It's a more approximate technique, and it's very popular in condensed matter theory. But you see, it doesn't work very well. I mean, it works exactly in infinite dimensions, but this is a 2-dimensional system, and there are severe deviations from the.
In a single band Hubbard model, if you go to such high temperatures, you know, you're say on the order of 10T or 5T, then, you know, as you explained yourself, do high temperature expansion, the lowest order in temperature would be linear.
Yeah, would be linear.
It's not surprising to see the tumors. It's actually surprising, maybe, to see why it goes down. It persists to lower temperatures. That's maybe the surprising.
Yeah, I mean, so if you go to temperatures large compared to the bandwidth, which would be 8T, so above the regime where we're exploring, there's this, like you're saying, this linear dependence that people understand. There's a linear dependence which people don't understand at very low temperatures, below what we can access experimentally right now. And then we're exploring this intermediate regime where we again see a linear temperature dependence. Okay. Okay, there's the violation of the MIR limit, but that, like you said, is because at high temperatures we expect this to just keep going on. That's not so surprising, but the linearity in the intermediate temperature regime is the main part. Okay.
Can I have a question? Did you measure the slope as a function of temperature?
Yeah, and
what do you get from the slope?
It agrees pretty well with what you would expect from like this Planckian models.
What Planckian models?
Where the resistivity is purely set by the temperature.
Well, that will give you an energy scale. What is that energy scale? Right. If you take the rho dt, let's say rho is units of e squared.
Over kBt.
What would be?
So it would agree with these h bar over kBt slopes that you would expect from.
No, there's a missing energy scale in those arguments. Right? In other words, you get an energy scale from that slope, right? You can the rho dt, right, has the units of h over e squared as for the resistivity, and then the temperature gives you an energy scale. And it's very interesting to know what that energy scale is. Those Planckian arguments are not microscopic in any way.
Mm-hmm. Okay.
Can you tell me what it is? I mean, can you?
I don't have it at the top of my head right now, to be honest. Maybe we can exchange emails.
That's a very interesting quantity because, okay, Nathaniel might tell you.
Yeah, I mean, there's a paper by Subir Sachdev where he looked at our experiment and a bunch of other experiments, and he actually has the slope in his paper. I just don't recall it.
Okay, there's an earlier paper by us, and we show that, okay, experimentally in Cuprate, that energy scale matches the TC maximum, which is something to do with superconductivity. In other words, as you change doping, that slope should change, or at least if you change the parameters, the super exchange essentially parameter also is related to that temperature scale. So that's why it's, it tells you something microscopic. And another question I have here, as long as I'm asking questions, did you try to see whether there's signatures of pairing at the temperatures you're looking at? Like, the whole correlations in your pictures, do they look like?
No, so far none of the cold. So there's like three experiments that are doing this, us in Munich and at Harvard, and none of us have observed any whole correlation. You might be interested in looking on the quantum gas archive just yesterday. It was by the Munich group where they studied these magnetic polaron correlations.
Yeah, I know that. Yeah.
But there's a new one yesterday that came out where they look at the interactions between the magnetic polarons.
Okay.
They're looking at the crossover from these magnetic polarons to Fermi liquids, and they still don't see the whole correlation in these experiments. They can see sort of things that are related to these whole correlations, but not yet. Like we haven't seen any bunching of holes yet. I think that seems to be still like at a lower temperature. Although like studies of TJ models seem to indicate that we're very close to the temperature scales where you start to expect to see it.
Oh, great. Okay. Thanks.
Okay. I wanted to talk a little bit about ARPAS in this talk, but I think I'm running out of time. Yeah. So let me just tell you that the other sort of interesting regime to explore obviously would be the Pseudogap, this regime where you expect the depression in the spectral function before you enter into the near the Fermi surface, before you enter into the superconducting state. And there was beautiful experiments, I believe maybe Yoav was even involved in them, in the group of Debbie Jin, where they developed these ARPAS techniques in analogy to condensed matter, angle resolved photo emission spectroscopy for continuum gases. And we've extended those now to lattice systems. So we've actually benchmarked them on the attractive Hubbard model. And we can see the pseudogap in the BCS crossover in the attractive Hubbard model. That's the part I just skipped over. The next thing one can do is try to study the doped Hubbard models and look for signatures of the pseudogap in these systems. And let me see, yeah, I have this graph here. This is a dynamical mean field theory calculations by Antoine George's group. And you can see if you extrapolate sort of to zero doping, the temperature scale where you see the pseudogap is roughly where the cold atom experiments are right now. So with a bit more cooling through this entropy redistribution ideas that we were discussing earlier, we might hopefully start to see some of this physics, changes in the topology of the Fermi surface. So we can probe all this stuff with condensed matter tools like ARPAS, but then we can also probe them to learn something new by looking at the correlations. So there I would encourage you to look at this paper that just came out yesterday. So with that, I'd like to thank you very much, and I'm happy to take any further questions. So also I want to thank, of course, the graduate students that did this work, in particular Debayan Peter and Elmer. And we've the postdocs, Peter Schaus and Stanley Merkondov, and we've had a lot of theory support from David Hughes at Princeton and several numerics groups around the world.
Thank you very much.
I'd be happy to ask a question.
Go ahead.
So I have a question regarding if you could kind of change the periodicity, would that change the point or the lowest effective temperature you can actually reach, if you could change it somehow, even adiabatically? If that would be a possible parameter, would that somehow enable reaching a regime of phase space which is harder to reach now?
I mean, I would expect in the end that, like, it's sort of, we like to talk about temperature in our systems, but they're closed quantum systems where entropy is the better thing to discuss. And I would think if you're like at similar entropies, then I wouldn't expect to see anything new. But yeah, I mean, maybe I'm wrong. Like maybe an adiabatic change can get you into something, into a more interesting phase. So at this point, like these entropies are limited, as I said, by the evaporation to about 0.4 kb per particle, but there's no reason why you can't go to much lower entropies. So the band insulators in particular have, Marcus Greiner has showed that they're at entropies of about 0.01 kb per particle, so 40 times less. If you can just start from these band insulators and isolate them, they have extremely low entropy, and then all you need to do is to change, like you say, the spacing of your lattice, and you can go from like 2 atoms per site to, let's say, 1 atom per site or less than 1 atom per site, maintaining this low entropy. And then I would think you can enter all these interesting phases at lower temperatures.
So these are entropy distribution tricks that you mentioned, or these are something else?
I mean, there's technical details of how you implement these ideas, but yeah, in general, like starting from a phase with a large gap, whether it is a mod insulator or a band insulator, something where we can really prepare a low entropy with respect to that, and then manipulate that to change the filling essentially to get into an interesting regime.
And maybe one more question. Did anybody use the quantum microscope to actually probe a bulk-like behavior? So essentially taking a bulk and just switching the single atom detection in the end to try and study correlation in a bulk system?
Christoph Solomon's group is trying to do that right now. No, not so far. Nobody has done that.
So I have a question. So I know that there's a proposal by Thierry Jamarki from some years back about how to measure conductivity in cold atom systems by shaking the lattice sideways and measuring energy absorption. I don't know if you thought about that at all or considered looking at that.
Like you want to measure an optical conductivity?
Yeah, it's optical conductivity, but I guess you could take, low frequency limit or something of that. Yeah, exactly. Like you shake at some frequency and you measure how much energy is absorbed.
Yeah, there's the group of Joseph Tyvison in Canada has been pursuing experiments in that direction. They have a few publications on that. So far, all their work is in a sort of a weakly interacting system. It seems it's challenging to kind of push it to the higher interactions, mostly technical limitations. That's why we had to go through this roundabout way of measuring resistivity.
I have a question. I'm a bit confused about something. Maybe you can help me correct. Aren't you just, your measurement, are you not just measuring the susceptibility, kind of this density susceptibility, basically? Right? You're putting on a potential of some.
Well, that's another thing you could measure is, there's the equilibrium physics. You could see how susceptible the system is to this charge density wave in terms of its density. So that's what we're seeing, I guess. If you just look at the density of the system, then you should be able to extract what you're saying. But we're going a step further. What we're doing is we're switching off this modulation and then watching the dynamics of the fermions as they diffuse after we switch off the modulation. So there you're getting dynamical information.
Yeah. You could have measured kind of a dynamical susceptibility.
So I guess what you're trying to measure is more like a compressibility at a particular Q vector.
If you know if you know the susceptibility for density modulation, then you using continuity equation, you can also extract current correlation.
I don't believe just this, like maybe we're not agreeing on terminology. So you just mean a static compressibility?
No, not a static.
Okay.
Yeah,
dynamical. Yeah, and I guess yes, what we're doing is related to a dynamical susceptibility. Yeah.
Because then you know, it might be a different experiment because you need to use some sort of, you did some sort of a quench, right?
Yeah.
Yeah, you could have used maybe kind of an oscillating, something like that, a potential.
Yeah.
And then you'd not need this, the way you extract conductivity is you measure separately, the diffusivity and the compressibility, and there's some assumptions that go in. For example, that equation and the Fick's equation. That's also, we can talk about that later. But I'm wondering whether you could have done an experiment where you just extract the current correlator directly without going through this, through this kind of diffusive assumptions. Basically, there's some assumptions that go in when you write this Fick's law.
Yeah. I think that's related to what I was the previous question. Like, you can use these oscillatory tricks, and people have been doing them. It's just there are technical issues with the measurements that prevent them from being pushed to higher interactions.
When you write this Fick's law, so you're making an assumption that that's what I'm trying to understand, is it an assumption or not? It seems like you're making an assumption that there's only two parameters, there's this gamma and D.
Yeah, it's a completely phenomenological equation there.
I'm wondering if you allowed another, for example, parameter there, would it change somehow the results?
Yeah, so it's basically like you're doing hydrodynamics with momentum relaxation.
Yeah.
It includes adding viscosities and all sorts of other terms. We just cannot resolve them within our experimental error bars. So if you start writing down the hydrodynamic expansion, there's there's all these other terms, and we don't have sufficient accuracy to extract these quantities.
Do you have a way to put artificial magnetic fields in the optical lattices, or that's a different technology?
I mean, people have been doing artificial fields. The main issue is, as we were discussing, these particles are neutral. So like if you're talking about Lorentz forces QV cross P, so those you get, usually the best way to get it in a lattice is by directly imprinting the piles phases. And so I mean, you have to use Floquet techniques to get there. And usually those come with a lot of heating.
Okay.
But I mean, it's something that people are working right now to try to find the correct parameters of the Floquet drive in order to keep the systems from heating to infinite temperature.
Well, another way, which I don't think was ever implemented, is to rotate the lattice, but that's probably too difficult, right?
I mean, it's something people are also pursuing. I mean, obviously the earliest work in cold atoms on like synthetic fields was rotation. Like people were stirring VECs and stirring Fermi gases and seeing all sorts of vortices and so on. And people now are trying to get into fractional quantum Hall regimes by stirring, again, just in more careful ways than earlier, try to reach the higher.
But that was never done with the lattice, right? That was only
with the lattice. It's I mean, nothing impossible, just somebody has to put the work. Yeah.
Okay.
Okay. Interesting. Other questions? So maybe just a question about this RPES. You said in this RPES, did you only do this kind of RPES measurements on the negative U Hubbard model? Is that right?
We've done it on negative U because it was the first time this RPES has been implemented in Lattice. So we had to figure out a lot of technical issues, and we wanted to benchmark it against something where one can do the theoretical calculations. The nice thing about the negative U Hubbard model is that there are no sign problems in the quantum Monte Carlo at any filling. So we could let me show you the results. We could extract these spectral functions. So for example, like this data here is for the attractive Hubbard model. Let's say it moderately weak interactions at this particular temperature, and then you can see the agreement with the quantum Monte Carlo done here. Then you can, we've done it as you increase the interaction, you start to see the gap opening from the chemical potential. So this is was for us to be able to compare nicely against quantum Monte Carlo, but there's no reason why this can't be extended to doped repulsive models, where there's the sign problem, and so you would have to trust your technique at that point.
And that's not this is not invasive. I mean, when you do this RPES measurements, can you do that without actually having a strong effect on the state itself?
Well, I mean, it's very analogous to what you do in condensed matter. You're just sending in a photon, it kicks out the atom. We put it in our case in a non-interacting state, so it just ends up not as if it's not in a. So we have like the spin up, a spin down, which are strongly interacting with each other, and then this atom ends up in a state that doesn't interact with spin up and spin down. And so it's as if it's ejected from the system, and then from the energy of the photon and the momentum of the ejected atoms, you can extract the spectral function, the occupied spectral function.
Okay. Other questions? Okay, if not, it's really, thank you for this really wonderful talk. Nice also to meet you in person. Well, not in person, but for Zoom. And yeah, hopefully we'll meet again soon.
Yeah, it was a pleasure. Thank you very much.
Yeah, great. Thanks a lot.
Thank you.